Hello and welcome to a very important episode where we'll be discussing about why ST elevation is there, when MI is there, and what exactly is current of injury. So we'll get right on to the topic. So as you can see over here in lead 1, 2, 3, in lead 1 we can see ST elevation over here, and the corresponding leads lead 2 and lead 3 we have ST depression. So this is just to acquaint you to what ST elevation and ST depression looks like. Okay, further things about this I've already discussed in a previous video about ECG and all that. Okay, and localization again, I'll put another video up for that. So the main aim for this video is to understand why ST elevation is there. So in general, when teachers are teaching or whatever is given in book, they mention these three things: rapid repolarization, delayed depolarization, and decreased RMP to be the reasons why there is an ST elevation. Okay, so nobody explains why exactly these things happen and how these things actually result in a current injury, which in fact results in the ST elevation. So that is the main aim of this video, to understand why these things are happening and how these are resulting in your current of injury. Okay, so before we begin, we'll just try to understand what is the importance of the ST segment. So over here, this QRS complex, that is when ventricular depolarization takes place. The T wave over here, that is where ventricular repolarization takes place. So in between that is your ST segment. So ST segment is that isoelectric part. So this actually corresponds to your plateau phase of ventricular action potential. So this is the ventricle depolarization begin here, ventricular depolarization has begun here, and this is the plateau phase, and repolarization, that is the ventricular repolarization. So this part, plateau, corresponds to your ST segment. And since this is depolarization, soon after that ventricular systole happens and there is ejection. So that actually happens during this part over here that you see. Okay, so this ongoing ventricular systole, ejection, and later ventricular repolarization begins over here. So this is the importance of ST segment. So this gives you a picture of what happens in this ejection phase, systolic ejection phase. Okay, so any abnormalities with this part will actually tell us that this ejection problem is there. Okay, stroke volume is not enough. So the blood that is there, now we'll come to understanding what happens. So you have potassium channel, because of the efflux of potassium, repolarization takes place, and that generates your RMP. And that RMP is maintained by sodium potassium ATPase. So these are two things that results in RMP and maintains RMP. So this sodium potassium ATPase, what it does is actively using ATP, it takes potassium inside, takes sodium outside. So net effect is potassium is taken inside. Okay, this potassium leaky channels generally take potassium outside. But there is one particular type of potassium channel called the KATP. So it is ATP dependent. So when ATP is there, this kind of blocks this channel. So again, potassium stays inside because of this. Okay, so because of ATP, potassium stays inside because the KATP channels are ATP dependent and keeps it closed. Also, ATP is required and used for sodium potassium ATPase. So that again keeps the potassium inside. So the net effect is keeping the potassium inside. Okay, what happens in MI? In MI, there is decreased flow. There's some blockade because of which blood flow is not there. Not enough nutrients, oxygen is not there. So because oxygen is not there, your whole production of ATP is impaired. Less ATP. Less ATP means your KATP channels are opened up, and less ATP means ATP is no longer there to keep the sodium potassium ATPase as active as before, so its activity declines. Okay, so these are two things that happen. So because of what happens, the ATP is less, sodium potassium ATP is not that active, so more potassium is there outside. Okay, potassium is there outside, and that usual formation taking potassium inside does not happen as much. And we have the KATP channels which are now going to open up because of the lack of ATP, because of which potassium is now going to go out. So in effect, what is going to happen? The EC of potassium will be increased and the IC of potassium will be decreased. Okay, just make note, I'm not talking of the absolute value. The potassium inside is much higher. It's like 140. Okay, outside is like 4. Okay, so here I'm not talking about the absolute value where ECF potassium becomes much higher than the ICF. That's not what I'm talking about. Compared to what was the ECF potassium earlier, normally now it slightly increases. And compared to what the ICF potassium normally is, it slightly decreases. That's all what I'm talking about. So don't confuse that. Okay. So what does this result in? So this is where you have to understand your equilibrium potential, Nernst potential. Why is your RMP minus 90? Because potassium channels are opened up during repolarization. Okay, the equilibrium potential of potassium is minus 94. So it comes to around minus 90. So that is why your RMP is minus 90, because the equilibrium potential of potassium is that much. Okay, so how do you calculate the equilibrium potential? That is with the Nernst equation. Okay, so I'm just leaving out the initial part RT by ZF. Those things are not changing over here. Log concentration of potassium inside by concentration of potassium outside. So what happened over here? The concentration of potassium outside increased slightly, but concentration of potassium inside decreased. Okay, so this whole thing, this decreases, this increases. So ultimately, what happens to this value? This value, because of this change, will decrease. So the equilibrium potential decreased. So say equilibrium potential was minus 90. Now instead of that, it's going to go to minus 70 because of this change. Okay, so because of that, instead of minus 90, this RMP comes little more higher. Okay, so this by default, by convention, we say RMP decreases. This is why again students might get a little confused. It's going more towards positive, so why is it decreasing? Okay, so it's not, again here the absolute value is what you're talking about. So from 90 it went to 70. So that is how this nomenclature is, so don't get confused with that again, because in textbook this is how it's mentioned. So when you're reading it, you might get a little confused. Okay, so RMP decreases means absolute value decreases from minus 90 to minus 70. That's what they actually imply. Okay, yeah, please keep that in mind because students always get confused with this. Okay, so RMP decreases because of this. So you understood why RMP is decreasing. Okay, next, rapid repolarization. So RMP decreases one thing. Next is rapid repolarization, something that happens. Why is that happening? Again, EC of potassium is a little more higher. Okay, so I previously put up a video about the changes in hypokalemia and all that. So in case you have a doubt about what I'm talking about now, please go refer to that. I explained it a little more in detail over there. So there are a channel called IKR. This not channel, the current because of the channel. Okay, inverse rectifying potassium channels. Okay, that results in a I current over here. Okay, so here it is ITO, transient outward, then IKR, over here IKS and IKR. So this is how normally the potassium channels are there. So this IKR somewhere is over here, here to here. So the thing about IKR is it requires extracellular potassium to keep it active. To open it up, it requires extracellular potassium. Okay, the extracellular potassium has increased. So more of them will get activated, which means more potassium is going to go out easily, which results in a rapid repolarization. Okay, along with that, we had already mentioned about a KATP. ATP is less, so KATP is open. So this, because KATP is open, more reason for potassium to go out. So because of these two reasons, because of IKR and because of KATP, what is eventually going to happen? Earlier phase 3. Okay, this is phase 0, 1, 2, 3. So 3 phase, and this is baseline 4. 3 phase becomes a little more earlier. So that results in rapid repolarization. So this is why in MI there is rapid repolarization. So we already covered why there is a decrease in RMP. We covered why there is rapid repolarization. Okay. Next is why there is a delay in depolarization. So you can see over here, this instead of it coming like this, it rapidly repolarizes from this point, early phase 3, and you can see that the RMP is not over here, instead it is over here, and it continues. Now depolarization should come. Why is depolarization delayed? So what is seen is that this decreased RMP that we were talking about earlier, because of the decreased RMP, the voltage gated fast acting sodium channels which are there, which are needed for activation. So from the threshold you have the voltage gated sodium channels. Okay, so because of that, their activity is inactivated because of the decreased RMP. Don't ask me how, I haven't figured it out yet. Okay, in case somebody who's watching this video knows about this, please mention in the comment section. I would love to know it. Yes. So anyway, decreased RMP will inactivate the voltage gated fast sodium channels. Okay. So this is a statement. Okay, we'll just try to understand what it means. So this is a membrane. These many sodium channels are there. Okay, and what happens is when the RMP decreases, inactivation of few happen. When RMP decreases further, again inactivation of more. So based on this, number of open sodium channels decrease. So depolarization will take more time because it's acting with less number of open channels. I hope you get that. Okay, so because of that, slope gets reduced, and this is how you'll see it, because it takes longer time with lesser active sodium channels. So as RMP keeps decreasing, the number of voltage gated sodium channels keep declining, active ones. So it gets more and more delayed. Okay, and even the amplitude won't be as high as before, because repolarization will happen in the same time. Okay, repolarization starting, the time delay is the same, that does not change. So whether it takes time or not, it just cannot reach that amplitude before. Okay, so this keeps on happening apparently at minus 55 millivolt. You know, the threshold value around minus 55 millivolt, almost all these channels are closed. So it just becomes impossible for the muscle to contract to this point, because you know there's no potential enough generated. Okay, so this is a more end stage that we are talking about. So I hope you understood why there is delayed depolarization. Okay, so this is a normal ventricular action potential, and to this ventricular action potential, because of MI, it comes out like this. So what happened here? Early repolarization. What happened here? RMP decreased, and a delayed depolarization. Okay, so these are changes that happen because of MI. So now that is done, we'll try to understand a little about current of injury. Okay, so current of injury, before we go to that, we have to understand normal RMP. Okay, so initially, because of the Gibbs-Donan effect, inside will be negative, outside of the membrane is positive, because you know proteins are large, they cannot move outside. So they will come and it'll be like negatively charged towards the inner side, and because of that, positively charged ions come and sit over the membrane. So that will be positively charged. So this is your normal RMP state. Imagine this part, okay, not this part is getting ischemic. We'll try to understand what happens because of this ischemia over there. Okay, the depolarization, repolarization during the resting state RMP. What happens is what we need to understand. So during depolarization, what happens to the membrane? The channels are opened up, positively charged ions come in. So that is basically what depolarization means. So inside is no longer negative, positively charged ions coming in. Okay, and correspondingly outside will be negative. So this is basically depolarization. During depolarization, what happens to the ischemic part? Because oxygen is not there, so there is delayed depolarization. We already established why this is happening. Okay, decrease RMP, inactivate rapid sodium channels because of that delayed depolarization. So what does it mean? This is becoming positive inside, but at the same time this ischemic part has not reached that level. it's much more delayed. Okay, it's not like it's completely negative, but still it's going to take longer to reach the same positivity. Okay, so relative to this, this is a little more negative inside. I hope you understand. Okay, so when we usually record ECG, we don't put an intracellular lead. Okay, we usually measure the potential which is there outside the cell. Okay, so the electrode is kept outside. Whatever the outside potentials are, what are recorded. Okay, so by convention, current flows from positive to negative. Okay, so electrons move from here to here, but current is by convention going from positive to negative. So that is because, you know, way back when current was first discovered and, you know, using wires, at that time the nature of electrons moving in current was not discovered. So at that time, by convention, the recording was taken as from positive to negative. So that's why by convention, you know, the flow of current is usually taken from positive to negative. Okay, so again, hope that does not confuse you. Okay, so from the ischemic part, it moves outside. So this is what happens during depolarization. When the ischemic part is there and normal parts are there surrounding it. Again, rapid repolarization. So during repolarization, what happens? So this is depolarized right now, right? So depolarization means inside becomes positive, outside becomes negative. During repolarization, what exactly happens? This goes reverse. Okay, so those positively charged ion like potassium is going to go out. Because it goes out, inside goes towards the negativity and goes towards the RMP. Okay, and positive charge ions went outside. So outside becomes positive. So this is generally what happens during repolarization. Okay, so now in this state, in one part where ischemia is there, we realize that there is a rapid repolarization. Why is that happening? Because of KATP and IKF. We already established that. So because of this, rapid repolarization is taking place. Rapid repolarization means, you know, this becomes negative first. This happens. Repolarization already happened. But in your normal part, that repolarization has not, you know, reached this level yet. So this is like the exact opposite of what happened during depolarization. Okay, so now here during repolarization, this becomes very fast. This becomes more negative. But by the same time, a normal thing did not, you know, result in repolarization to this level at this point. So compared to this, relatively, this is still more positive. Okay, I hope you understood that. So now again, from positive to negative, that is how the current is going to flow. Okay, so it goes outside again. So during depolarization, during repolarization, the current is going from the ischemic to the outside part. Okay, I hope that is clear. Now let's come to the state where it is rested. So in the diastole after, you know, repolarization, now it is resting. Okay, where it's reached the resting membrane potential. So we already know that resting membrane potential decreases. Why? Because KATP and sodium potassium ATP is lesser and ATP is active. Okay, so what happens normally during RMP? First slide that I was talking about when I was talking about current of injury, inside is more negative, outside is more positive. This is what normally happens. But over here, the RMP you can see is decreased. Instead of, you know, minus 90, it's at minus 70. So that means there is more, relative to this, there's more positive charge ions over here. I hope that is clear. Okay, you need to understand the basics of your channels and all the initial steps of nerve muscle physiology to understand all these things. Okay, so here this is how it's going to be because of decreased RMP. So now as you can see outside, what is happening? The ischemic part is negative, the normal ones are positive outside. So current is going to go from outside to inside. So over here it's this way. Okay, so this is a table that is from Ganong's textbook. Okay, so as you can see, rapid repolarization results in out of the infarct. Okay, so ischemia is there. After that, that cell that we are talking about has gone into infarction, and from that infarcted part, the current is going outside. Again, depolarization, delayed depolarization, that also results in movement of current outside. Okay, so this is already established. So because of both of these things, ST segment appears elevated. Over here in the resting phase, it's moving into the infarct. Okay, so actually what happens is, because of this, the TQ segment is depressed. But when you actually look at the ECG, what it manifests as is the ST segment elevation, because this part is lower. So because of that, when you look at it, it looks like the other part is elevated. I'll just try to explain what it is. Okay, so this is RR interval. You can see this is the T wave, this is the QRS. So T, after that, this along with this is your TQ segment. Okay, generally we say segment does not involve a wave, but over here this is how TQ segment is given. Okay, so the P and the PQ segment and the TP. Okay, so all these together is what forms the TQ segment, and this is your ST segment. So if this is lower, this part is lower, when you look at it, it seems like this part has gone up. Okay, so just take a look at this over here. Over here, you can actually see that over here what happened is this part actually went down. But it looks like, this part has gone up. Okay, so anyway, because of all this, finally it looks like ST segment is elevated, and these are the reasons for this. I hope you understood this now. Why ST segment elevation is seen, why there is rapid repolarization, why RMP is decreasing, why delayed depolarization is there, all the ionic changes that happen, why, and because of that, how is current of injury produced, what is current of injury, and again, how that is resulting in ST segment elevation. So this is very, very, very important to understand this, because you'll come across this throughout your life. Okay, so hope this was helpful. Thank you.